and gentlemen, welcome back to the 2020 International Seminar on Intelligent Technologies and its Application, ISITIA. We are still broadcasting live from Electrical Engineering Department, ITS, Surabaya, Indonesia. In the morning, we had ISITIA officially opened by the Dean, continued by the technical session. I hope all of you are excited to have the keynote session after this. Ladies and gentlemen, before we continue to the next agenda, which is the keynote speeches, we would like to ask all of you to take a moment to remember the passing of Dr. Istas Pratomo on 28 June 2020. Dr. Istas Pratomo was an inspiring lecturer of the Department of Electrical Engineering, ITS, who was the chair of ISITIA 2018, which was held in Bali. He was full of initiative and kind-hearted. He died at the age of 40. Let's take a moment to pray for his departed soul to rest in eternal peace. Thank you very much. Now, to get you excited as well as informed about ISITIA 2020, Dr. Prihastiti has prepared a short informative video for you. Let's take a look on a bit of statistics from ISITIA 2020, in which you are taking a part now. Let's give applause to everyone in ISITIA 2020. Very interesting and exciting video from Dr. Prihastiti. I hope you are warmed up again to continue to one of the main agenda of ISITIA 2020. I would like to invite Professor Mochamad Ashari, Director of Institut Teknologi 10 November ITS, to welcome our keynote speakers as well as the attendees. Ladies and gentlemen, Professor Mochamad Ashari from ITS.
Vita. Assalamualaikum warahmatullahi wabarakatuh. Good morning, good afternoon for ladies and gentlemen. Yeah, I have to mention many time zones because we are now have a keynote speech that we are in Indonesia as the center of the meeting. So our respected guests and keynote speakers, colleagues, and all participants, good morning, good afternoon, and good evening, all together in our session today. First of all, I would like to express our gratitude to our respected guest keynote speech, also for the Dean of Intelligent Electrical and Information Technology, the Faculty of Electric, we call it Electrics, Intelligent Electrical and Information Technology, and all the committee, the chair, respected and distinguished participants. It is a pleasure to welcome all of you in this virtual event of 2020 International Seminar on Intelligent Technology and its Application, ISITIA. It is very interesting today because we have 3 different time zones in the world. Yeah. I would like to express my gratitude to Dr. Ardyono for representing researcher and taking a part in ISITIA today. Yeah, good afternoon, Pak Ardyono.
Pak Ardi belum.
Still mute, Pak.
Yes.
Okay. Also, I would like to convey my express to Professor Haiping Professor Haiping from Wollongong. Good afternoon. Yeah. How's the weather in Australia now?
Yes.
Okay, thank you for joining us. Thank you for gave a guest lecture for our conference today. I think now in Wollongong, the time is 3 hours ahead of Indonesia, of Surabaya. So I think it's around 4 or 5 o'clock, yeah, in the afternoon.
Yes, yes.
Okay. And then also I would like to thank Professor Natasha Maurits. Professor.
Thank you.
Okay. Good morning.
Good morning.
Early morning for you.
It's 8 o'clock in the morning here.
8 o'clock in the morning. Yeah. How is the weather now in Netherlands?
It's not so bad, actually. There's a little sun shining. So thank you for asking.
Okay. Thank you very much for give keynote speech in our conference today.
It's an honor. Thank you for inviting me.
Thank you. I think it's very nice. This is our first experience during the pandemic COVID-19 to arrange this kind of conference with 3 different time zones.
It's a challenge, but I'm sure it will be a very nice meeting.
We hope so. Okay, so ladies and gentlemen, we are now under serious impact of COVID-19 in Indonesia, in Surabaya, especially the condition still disparate. Yeah, we are still against COVID-19, but ITS as the Institute of Technology, we try to contribute more and more to support the government by presenting the innovation of technology. During this COVID, or we can say that for the last 3 months, we gave or we present some innovation technology, especially for medical field. We have a collaboration we strengthen our collaboration with a hospital in Surabaya or East Java, and also hospital in other places in Indonesia. Ladies and gentlemen, ITS, we have a vision that to be the world-class entrepreneurial university. We just restructure our faculties from 10 faculties into 7 faculties. 7 faculties, and also we build 10 research centers that all the faculties, research centers, and also technopark, science technopark, we have 4 clusters. All this organization we put on in line with Industrial Revolution 4.0 technologies. For example, our faculties, we have a big data, we have intelligent technology, which is embedded in these faculties that the host of this conference, a Faculty of Intelligent Electrical and Informatics Technology. We have also new material. We have also many things, including the defense and biotechnology. So all the faculties and 10 research centers and also technopark, we restructure in line with Industrial Revolution 4.0. So during the COVID-19 started in Indonesia is around March this year, we are very suddenly this comes, and then we try to innovate whatever we can do. And then what happened is during the last 3 months, we are very proud that we could produce personal medical equipment for prevention, like face shield, because the hospital in Indonesia is not ready yet. Then we try to help to build, to modify our classrooms. Our classroom in ITS, we modify as a workshop to produce the face shield. And within 3 months, we successfully to produce 170,000 pieces of face shield. And then we donate to many hospitals in Indonesia. We also suddenly within 2 weeks try to build a robot. We call it robot for robot assistant for hospital. We call it Raisa. This robot is dedicated for hospital. We have already delivered 7 robots to 3 hospitals in Indonesia. This robot is very helpful because can be loaded up to 50 kilograms for delivering clothes, food, medicine, and others. Yeah. And then this robot is controlled removed by the nurse. So it prevents the transmission of COVID between the patient and the medical person. Ladies and gentlemen, so many products within 3 months we produce it. I think it's more than 25 items, including a booth for PCR tests, and then etc. Like the design of emergency hospital, and also a ventilator, etc. We try to do our best within 3 months, and then thanks to God that everybody here in ITS work using our technology to innovate and then deliver to the people. Respected ladies and gentlemen, we are very happy today for this conference because this is a part of our vision to be the world-class university. And then we would like to extend our collaboration. We know that we have already collaboration with Wollongong, with Groningen. Some of our professors, our lecturers graduated from those universities. So we would like to extend this collaboration. Ladies and gentlemen, so through this conference, I hope that not only we will have the opportunity to see the idea, the finding from other researchers, to exchange the knowledge, the recent development, the recent finding of technology between us, between researchers, between academia and also the students, but also we would to show you what kind of ITS moreover. But unfortunately, because of the pandemic COVID-19, we could not arrange this conference by physically comes. So it would be much better. You can enjoy Surabaya if we conduct the conference physically, but unfortunately, because of the COVID-19, it shall be conducted by virtual. So ladies and gentlemen, ITS, we have many collaboration programs, especially for international program. We have already established undergraduate international class, almost all department we have. And then many students comes from abroad also. So welcome students from abroad to join ITS. You can join in a degree program, like in international undergraduate program, or in master, or even for short-term program, for student exchange, for research, for many kind, even for 2 weeks, just to extend our collaboration. And also we are ready to send our students abroad to give more experience for our students. Ladies and gentlemen, this year also, we launch a master and PhD bioresearch. This program hasn't been launched before in Indonesia. So this year, we are happy to serve master bioresearch and PhD bioresearch in ITS. So again, I would like to invite you, all the participants, to explore the ITS, to explore our program, and to extend our collaborations. Many technology, many innovation has been produced by ITS, like the movie in the background of my wall here. Again, in this moments, I would like to express our gratitude, especially to distinguished guest speakers, distinguished invited speakers, the committee, the chair, and all participants. Thank you very much. Enjoy ISITIA. Enjoy this virtual session. Wassalamualaikum warahmatullahi wabarakatuh.
Thank you, Professor Ashari. Ladies and gentlemen, now for the keynote speeches. This afternoon, we will have Professor Imam Robandi from the Department of Electrical Engineering ITS as the moderator. Good afternoon, Professor Imam.
Good afternoon. So, yes.
How are you?
Okay,
Fine?
thank you. Fine. It's okay.
Okay.
Now in my home.
Yes, perfect. Okay, so ladies and gentlemen, I will leave this session to Professor Imam Robandi. Professor Imam Robandi, time is yours.
Okay, thank you so much, Dr. And also, okay, ladies and gentlemen, good afternoon today. Thank you for our President, Professor Mochamad Ashari, for welcome speech. It's very nice welcome speech today. So, good afternoon, all of the participants. This is the time of Surabaya in afternoon. So the first I would like to express my guest speaker, special Professor Haiping from Australia. I don't know the pronunciation is okay or not. Haiping. Yes.
Yeah, correct.
Yes.
That's good.
Yeah, so sometimes the pronounce from Chinese characters is very difficult. Yeah. Also, my honorable guest, Professor Natasha Maurits. This okay? Our
Thank you.
pronunciation for Natasha?
Yes,
Yeah?
yes, that's fine. Thank you very much.
Are in Netherlands. Okay, the last Dr. Ardyono Priyadi, the special guest from our home, from ITS. How about you?
Thank you very much, Professor Imam.
Yeah, now we have three great speakers in this session. So the first, I would like to invite Professor Haiping. Yeah. Before that, I would like to read I brief the small CV from the Professor Haiping. Professor Haiping received the PhD degree in mechanical design and theory from Shanghai Jiatong University, China, 2002. Professor Haiping was a research fellow with the University of Technology Sydney, 2005 until 2009. And he was also a postdoctoral research associate at Imperial College in London, 2004 until 5. And the University of Hong Kong, 2002 until 2003. And now he is a professor at School of Electrical, Computer and Telecommunication Engineering, University of Wollongong, Australia. Also, he is a subject editor of the Journal of Franklin Institute, an associate editor of IEEE Transaction on Industrial Electronics and IEEE Control System Society Conference, and an editorial board member for some international journal. Now his research interests include vibration control, vehicle dynamics and control systems, robust control theory and engineering application, electric vehicles, robotics, automation, smart materials, and structures. Wow, so many major. Okay, Professor Haiping will talk about advanced suspension control system design for vehicle and driver ride comfort. So you have 30 minutes from now for presenting your idea, your lecturing, maybe. Now we start from 1:26. Yeah, in my watch. Yeah. Okay, Professor Haiping do. So welcome. Good luck for you in presentation. Thank you.
Okay, thank you. Yeah, can I share my screen? Yes, thanks for the chair's introduction, and it's my great pleasure to be invited to give this keynote speech. And my topic today is advanced suspension control system design for vehicle and driver ride comfort. And first, I will give a brief background about the suspension systems, including passive suspension system, active suspension system, and the semi-active suspension system, and also about control system for the suspension. And then I will talk about vehicle suspensions with traditional MR damper and also with variable stiffness, variable damping, MR damper respectively. And after that, I will talk about seat suspension system, including active seat suspension, semi-active seat suspension system with a rotary MR damper and also with electrified devices. And finally, I just give a summary about that. As we know that vibration caused by an uneven road can be reduced or controlled by vehicle and the seat suspension system to improve the ride comfort for drivers, passengers, and cargoes. Generally, suspension system can be classified into three types. They are passive, active, and semi-active suspensions. Here we have two figures. One is showing vehicle suspension system. Another one is for seat suspension system. So if you are not quite familiar with them, maybe you can have a look at the two pictures. And for passive suspension system, it's quite simple and also very cost effective. Generally, passive suspension system consists of just a spring and observer, or we call damper. But passive suspension system cannot provide the controllable damping force to meet different requirements under different conditions. So that's a disadvantage of the current often used passive suspension system. And to overcome that disadvantage, so we have another two types of suspension system. The active suspension system, which can provide active force output to meet different requirements and also to provide a better ride comfort. But the disadvantage associated with the active suspension system can be like high power consumption, expensive hardware, and also the high requirement for the space. And this picture shows the active suspension system which used linear electromagnetic motor. And certainly for active suspension system, it can also have actuator like hydraulic actuator or other types of actuator to provide the active force. So this is another suspension system. And the next one is semi-active suspension system. Semi-active suspension system can provide both reliability of passive suspension system and also the effective control performance of active suspension system without higher energy requirement. And MR damper, that is a magnetorheological damper, is often used as a semi-active suspension system as a damper or observer because it can provide the variable damping property. And maybe not everyone is quite familiar with this MR damper, so perhaps this slide can show the principle of MR damper, which is based on magnetorheological fluid. And for the magnetorheological fluid, its property can be controlled if we apply magnetic field, okay, to change the property of that, so that the fluid can become as a liquid and semi-solid or solid, and so that its damping property can be changed. So here we have the animation to show the principle of that MR fluid, and maybe you can use that to understand why we can use MR damper as a damper for the semi-active suspension to provide the variable damping property. And in terms of performance requirements for the suspension system, and we can see that there are three main performance requirements we should consider. The first one is the rate comfort. Certainly that is the most important one, because we want to use the suspension system to isolate or reduce the vibration so that we can have a rate comfort. And the rate comfort can be evaluated in terms of sprung mass acceleration for vehicle suspension system, or can be used as a driver head or body acceleration if we consider that for seat suspension system. Another requirement is about suspension travel space, or called deflection, okay? Because for any suspension system, certainly we have very limited suspension travel space, so that we have this requirement for that. And also road holding capability. So this is mainly for vehicle suspension system, because suspension system can be also used to keep this capability to make sure the stable control of the vehicle. And in terms of evaluations for the performance of the suspension system, we can do that in both frequency domain and time domain. In frequency domain, we consider to evaluate frequency response of the suspension system under random road input. And in time domain, we consider the system response in terms of different road inputs. For example, we can use bump road input or random road input to evaluate the system response and to see whether the performance can be satisfied or not. And before we consider to design the suspension system, and also in particular to design the control system for the suspensions for both active suspension system and semi-active suspension system, we should have the model of the system. And we take, for example, the quad cast suspension as an example here. And if we are going to design, for example, a control system for this suspension system, we should have the mathematical model in terms of differential equation based on Newton's second law. We have this equation to be built to model this system. And if we are going to design the control system for this suspension system based on state space model, then we need to convert that differential equation into state space model. And if we consider all those performance requirements as mentioned in earlier slide, for example, acceleration, so we can define one objective as acceleration. So that is the main objective to achieve. And also we need to consider suspension deflection as a constraint, and also road holding capability in terms of dynamic load of the suspension system. So we can define these two constraints into another objective. And if we are going to apply the different control strategies, for example, H infinity control, to find the best control system, and we may design the controller as a state feedback controller, and then we want that controller to achieve this objective to minimize the H infinity from a performance requirement from the disturbance to the first objective, subject to the constraint for the deflection and the road holding in terms of dynamic load. So this is a basic description about mathematical modeling of the system and also for the controller design or control system design. And when we design the control system for the suspension system, we should consider many practical issues so that our designed system can deal with those issues if we want to implement the control system in reality. And the issues could include, for example, parameter uncertainties. Okay, because for the suspension system, it will have a spring and damper, and this spring damper, their parameters could be changed when they are used under different conditions, or could be changed if we use them for quite a long time. Okay, and also the change of the load. Okay, for the passenger car, the number of passengers will affect certainly the performance of the suspension. So we should consider this uncertainty. And some other issues, for example, input time delay caused by actuator or the computation time, actuator nonlinearity for actuators such as electro-hydraulic actuator, actual saturation, and all the actuators should have the limit output. So we need to consider that into the controller design or control system design. And some also practical issues like measurement noise, actuator and the sensor fault, and also other nonlinearities and uncertainties. We should consider them when we design the control system. And to consider those objectives and also the practical issues, really there are many different control strategies could be considered. For example, to deal with multiple objectives, and we can consider to have multiple objective control based on LQR control, based on H infinity control, or based on some combinations of like H2, H infinity, generalized HL2, generalized H2, and so on. And also we can consider to use constraint control to deal with multi-objective trade-off. For example, we can consider to minimize one objective subject to other constraints. Okay, so we can have different control strategies to be considered. And to deal with those practical issues, we also can consider to have a robust control and also nonlinear control, adaptive control, and fault-tolerant control, and so on. Okay, and in terms of availability of the state variables, and we may have a state feedback control, a static output feedback control, observer-based state feedback control, or dynamic output feedback control, depending on whether this state variable is available or not, and we can have the choices. Okay, I just gave you that brief background. Now I take a vehicle suspension system with a traditional MR damper as an example to further discuss vehicle suspension system. And as mentioned that for this suspension system, we should also start from the modeling. And we also take the quad car suspension system as an example here. And based on Newton's second law, we have this suspension system model to be built. And then here, because we are using MR damper, so we need to have the MR damper model to be involved here. And here we normally use the Bokman model for the MR damper. And you can see from this Bokman model that MR damper is really highly nonlinear devices. And it will certainly have this problem for the control system design, because we need to consider how to deal with this nonlinearity caused by this MR damper. And for the control strategies, and some different control strategies can be considered for this suspension with MR damper. For example, bump control. And for this control strategy, we should define the desired force first. And the desired force can be obtained by using, for example, skyhook control strategy and ground hook strategy, or hybrid of both skyhook and ground hook strategy. After we get this desired force, which is required to let the MR damper to generate, and then we can calculate the voltage or current to be applied to the MR damper, because the MR damper is actually controlled through the control the voltage or current to be applied to the MR damper. So we use the desired force and the actual force generated from the MR damper, then we calculate the voltage to be applied, and then we can use this voltage to control the MR damper to provide the approximate the output force to the desired one, so that we can get improved performance. We can also use a inverse model-based control strategy. And in this case, we still need to have a desired force to be calculated. And then we need to calculate the voltage or current to be applied to the MR damper based on the inverse model of the MR damper. And for the inverse model, we can use also different ways. For example, if we use polynomial model to model the input and the output relationship of the MR damper, so we can get its inverse input, which is the current, and we can get that and then apply this current to control that MR damper. We can also use other ways. For example, we can use a neural network to model the inverse input of the MR damper. And also we can use a fuzzy model to get the inverse input of the MR damper, so that we can have the current to be generated based on the desired force, based on the inverse model, and to apply that current to the MR damper. And this slide shows a block diagram about how to use that inverse model to control MR damper. And you can see from this diagram, you can see the signals are measured from the suspension system, and the controller will be used to calculate the desired force. And then based on inverse model, we calculate the current, and the current will be applied to the MR damper to vary the damping property of that MR damper. And this is a block diagram for that inverse model-based control strategy. And this diagram plot shows the some result obtained based on this control strategy and the comparison between semi-active control, active control, and passive suspension. And compared to the previous two strategies, we have another strategy to be considered that is called direct control. And for the direct control, we do not need to calculate the desired force first and then calculate the voltage or current. And for direct control, we can directly to get the voltage or current to be applied to the MR damper. And for this strategy, we also can have some options. And here we consider to use a robust control. And for this case, we can have this nonlinear model for MR damper to be involved in the model of the system, but we regard the nonlinear terms inside of this MR damper as external disturbances. And then we can use a robust control to design the controller so that the control system can be robust to those disturbances, which are actually caused by those nonlinearities. So this is one direct control strategy can be considered. Another one is a TS fuzzy model or TS fuzzy control. In this case, we still use nonlinear MR damper to be in the model, but for the nonlinear terms, and we can use a TS fuzzy model approach to model them so that finally the nonlinear model can be represented by a set of linear models based on TS fuzzy approach. And then we can design a TS fuzzy controller to deal with these nonlinear terms, and so that we can get the current or voltage of to be applied to the MR damper directly from this approach, and then control the system to get the improved performance. And for the suspension with the MR damper, and certainly you can have the available MR damper in the market to be used, or you can design the MR damper by yourself. And here, our group designed the MR damper to suit the requirement of the suspension system. And here is a design diagram, and here is a prototype of our designed MR damper. And this diagram shows the measured parameters and also the comparison to the simulation model, and so that we can use them to design our control system and to let the system to be tested. And this slide shows the test setup, and we have the quad car suspension system to be built, and also we have MR damper together with the spring to be installed, and then we have our measurement system and control system to be connected, and then we provide the road input and then measure the relevant signals, and then use a controller to control the suspension system to get the response to be recorded. And this slide shows the test result on the in the frequency domain, and then we can see that compared to the passive suspension system, the semi-active suspension system with MR damper really improves the performance. And here we use two different control strategies. One is a scaffold, another one is a gas fuzzy control. And for these two different control strategies, the performance has a little bit difference. And you can see that really the control strategy will be also very important for this suspension system design with MR damper. And here shows that the result under the bump input in time domain, and we can see that the acceleration of the suspension system is reduced by using the semi-active suspension system with MR damper. And this slide shows the random response. The input is a random road input, and also we can see that the suspension system performance is improved compared to the passive suspension system. We know that mostly people consider semi-active suspension system by using MR damper, but most of them, they only consider to use the very damping property of the MR damper. But for the suspension system, and we can see that the variable stiffness can also take a very important role in improve the performance. And many people also have made effort to design different devices with the capability of variable stiffness and variable damping, but most designs are quite complicated and may not be quite suitable for the suspension system. And by observing the past, the problem with those designs, and we designed a new device and based on the MR damper, and so that this device can have a variable stiffness and variable damping capabilities. And this design actually is based on two MR dampers. And you can see here, this is a MR damper which is used to vary the damping property like traditional MR damper. And here we use another MR damper, and this damper is actually used as a switch or as a connection to connect these two springs. Okay, we have a spring 1, spring 2, so that the spring and also the overall stiffness of this device can be varied depending on the control of this MR damper. And this is a prototype for that design, and this is the test for the parameters of that prototype. And then we further analyze this system with a newly designed variable stiffness, variable damping MR damper, and we have the model to be built based on this system description. And you can see that we have this new device to be included in this model. And based on Newton's second law, based on the model of the MR damper, and so on, we can have the mathematical model to be obtained. And for the controller design for this new system that will be also challenging. And in this case, we can see that we have two MR dampers to be controlled. And one MR damper is used to vary stiffness, another one is used to vary the damping. So we have two different control strategies for the two different MR dampers. And for example here, and we can consider two situations. One case that we just keep the stiffness as a maximum one. Another case we can consider to have the minimum one. And we know that by varying the stiffness, the system resonance frequency could be varied, so that we can use that capability to shift the resonance frequency to avoid the resonance with the input frequency, so that we can have the vibration to be reduced. So that's the principle based on why we need to vary the stiffness. And this is a block diagram to show that how to control these two systems and to have the system performance to be improved. And here's
excuse me, just 3 minutes.
Yeah. Okay. Right.
Just 3 minutes.
Okay, thanks for the reminder. So maybe I can go quickly about the following slides. And so the test results shows that this new device really get the improved performance compared to the variable damping only case. And then we move to the seat suspension system. And similarly, for seat suspension system, we have three types of system to be applied. And but for most seat suspension system, they use a linear actuator or linear dampers, so that will not let the seat suspension system to be really implemented in for the real product. So we propose to use a rotary actuator and a rotary damper to replace the linear one, so that the new design can be really implemented in practice. So this is a rotary actuator, which is just a conventional motor. And this is a rotary damper based on MR damper. So that is a rotary one. And also it's different to the linear one. And based on the rotary actuator or damper, so we can easily to install this actuator and dampers into seat and to control the system, so that the system structure is simple and the price is also lower compared to the linear one. And first, we have a look at the active one. We use the motor as an actuator, and we have the control strategy to be applied, and we have measured signals to be applied. And here we have a friction estimation to compensate the friction, so that performance can be improved. And also to test that system, we have the test setup to be used. And here we have the seat. We have the platform, which is used to provide the excitation to simulate the vibration. And this is a photo shows that test rig, and maybe you can speak that. And here we have the result given by as shown in this video, short video. And this one is a controlled one, that is active suspension system, and this is a non-controlled one, a passive one, and we can see the difference between these two systems. And the active seat suspension system really improves the performance and vibration. And for the rotary MR damper, similarly, and for the linear one, as I mentioned, and it has a high requirement, and also the design is not so easy. So we designed a rotary one, and use this one to replace the linear one and to be applied to the seat suspension system. And this is a prototype, and we install this rotary MR damper here, and it can be easily out there. And we get the performance, and based on the test result, we can see really the semi-active seat suspension with the rotary MR damper improves the vibration performance. And so this also another result shows the reduction percentage based on the semi-active suspension system. Okay, lastly, I just quickly to introduce our recent development in this area, and we have a semi-active electromagnetic damper to be developed to reduce the vibration, and this damper can vary the damping property of the system based on the conventional motor, but here we use that electric circuit to vary the load, and it can be easily implemented, and also the energy consumption is very low. Another one is a variable stiffness seat, and in this case, it's also based on electric circuit. And here we use the inductor and also the resistor to vary their parameters so that the stiffness and the damping property can be varied for this system. So it's based on the motor again. So that's an electrified device. And the last one is a variable inertance state. And in this case, we use the motor as a connection and to control the force of the motor to say that here we have two flywheels so that they are connected or disconnected based on the control of this device, so that the inertance of the system can be varied, and then it can be used to control the system performance to reduce vibration. All these systems are related to the control system design, but here I will not give you the more details, and if you are interested in that, and you can find all the details from our recent publications on these topics. Okay, and so here I gave a very brief summary, and you can see that both active and semi-active suspension system can be used to improve the vehicles and the ride comfort performance. And control system design is quite important for the implementation of both systems, and in particular with the challenging issues such as linearity, constraints, and the disturbance, and so on. And for improve the ride comfort, electrified suspension system was attention to due to faster response, high control capability, and less power consumption. Even I just quickly go through those three devices, but to us, we think that these electrified systems are very useful and can be used for future research. And also lastly, the integration of passive, semi-active, and active systems can take advantage of all of these systems and improve the ride comfort in broad range with less power consumption. So needs more investigation. So that's all for my talk, and sorry for the rush because of the time. Any questions I would like to take?
Okay, thank you so much. So we have around 10 minutes exactly. We have around 50 minutes, but you need more than 30 minutes. So Professor Haiping discussed about so many control, from the conventional control, feedback, differential, polynomial, until the very complicated control, bank control, LQR, and others. So let's discuss together. You can use chatting or directly raise hand.
So you mean the tracking control?
Yes, yeah, okay. Raise hand from Jati Jamari. Jati Jamari from, okay, please.
Yes, my name is Jati from Sampurna University. Thank you very much for your presentation, Prof. Du Haiping. I'm very interested with your work. When you are using the suspension under the seat, I see that when the control works, the movement of the person on top of the seat is likely out of phase with the movement of the vibration below the seat, right? And my question is about, what about the handling of the overall vehicle when we apply that suspension under the seat? Because it seems that, you know, we cannot really feel what happens with the road if we fully filter out all of the, you know, movement that is felt by the tire itself.
Okay, enough. Okay, Professor Haiping, please, about handling.
Okay, thanks for your question. And I think that maybe due to the network issue, I missed a few sentences said by you. But generally, based on my understanding about your question, that you are asking about that the video which shows the vibration reduction for the person sitting on the seat. And so you say that the person sitting on the seat, that the vibration under the seat is provided by the motion platform, which can be used to simulate the road input. And but for the seat, you know that the seat is not directly connected to the road. Actually, it normally will be sit on the car, and so the vehicle suspension system is actually the direct connection between the car body and the road. So when we use that platform to simulate the vibration to be applied to the seat, and we need to consider the signal actually is after the vehicle suspension system. It's not the direct use of the road input.
So yeah. That means in your research, you only created the modeling from the suspension or all of the body of the car. You have been created in all of the model in state space.
Sorry, I cannot get the point, the question.
So the voice is not so clear. So sorry. Okay, you created the modeling in state space model. Okay.
The model of the system.
Yes.
You mean the model for the seat or for the which model? Sorry.
Because I look at in your model is very small. The dimension around 3 or 4. That right?
So you mean that model is very small?
Oh yeah. Okay. The next question, we have 4 minutes. Another. Which one? So I check. Ahmad Arifin, raise hand. Ahmad Arifin, okay.
Okay, thank you, Prof. Imam. I straightforward to express my question to Professor Haiping. Okay.
Yeah, thanks.
Okay, very interesting research and.
So you introduce yourself from where?
Okay, I'm Ahmad Arifin from Faculty of Electrical Intelligent Electrical and Information Technology, ITS. I'm serving as a biomedical engineering department head in our faculty. I also interest in your model because I also work in fuzzy control. And in your presentation, you present such kind of the Takagi Sugeno fuzzy model. How do you perform such kind of transformation from the real damper and spring in your plan to the linear of the fuzzy Takagi Sugeno fuzzy model? Okay, thank you.
Okay, thank you, Professor Haiping. Please.
Okay. Yeah, thanks for your question. Yeah, that's quite interesting. And actually, we can have two. You know that for the fuzzy model, we can fuzzy method. We can have two different fuzzy methods. One is just like a fuzzy logic. So in that case, that is a model-free control method. And in that case, no matter it's a linear model or non-linear model because it's model free. So you just need to define your fuzzy rules and to deal different situations and to design your controller. And so fuzzy rules will be very important for that case. Another fuzzy method is here in my slide, that is a TS fuzzy model. Actually, it's still a model-based fuzzy strategy. And in this case, its principle is try to convert the nonlinear system into a set of linear systems. And so by using this method, you need to identify some nonlinear terms in the system. And then based on we call a sector nonlinearity method to define the range for the nonlinear term. Okay, so for each nonlinear term, you can have a minimum value, maximum value, you have that range. And if you have more nonlinear terms, so you define all of that. And then you can have that combination of different ranges, and then you can combine all of them together based on the fuzzy rules. And then you convert that nonlinear system into a set or linear systems. And then you just need to design the linear controllers. So in that case, you can deal with those nonlinear terms and to get the performance to be optimal for that system.
Okay, Professor Haiping, the discussion is very interesting.
Okay, thank you very much, Professor.
Yeah, but the time now is enough for our discuss. Thank you so much, Professor Haiping. So until next time, we can meet again in another session. We give applause together for Professor Haiping. Okay, thank you. The next session for Professor Natasha Maurits from Netherlands. So I would like to read the CV from the Professor Natasha. Professor Natasha graduated from the master degree in 1994 in applied mathematics and PhD degree in 1998 from biophysical chemistry. She is full professor of the clinical neuroengineering at the Department of Neurology of the University Medical Center Groningen, Netherlands, UMCG. That's correct, Groningen or Groningen? Groningen.
Oh, Groningen, very good, very good.
Oh, Groningen, yes. As well as the Chief Scientific Information Officer, the heading section Information Management for Research, Education and Training of UMCG. She is also visiting professor at Strathclyde University in UK, and University of Lincoln, also in UK. Her research focuses on clinical neuroengineering, in particular biomedical signals analysis, multimodal neuroimaging, high-density EEG recording, visualization of high-dimensional data, and home-based diagnosis and monitoring with application in neurology and cognition. Yes, published more than 140 international peer-reviewed paper as well as 2 books. From the neurology to the methodology and back, an introduction to clinical neuroengineering, published 2012, and Math for Scientists, Refreshing the Essential, published 2017 by Springer. She is a senior member of IEEE, member of the advisory board of School of Mathematics of the University of Groningen, UOG, member of the Scientific Advisory Board of the Lincoln School of Mathematics and Physics in UK, and chair of the Dutch Biomedical Engineering Conference. Now she is very interested in the Go Fair initiative, personal health, environments, medical and care, data coupling and sharing, and its ethical and legal implication. Wow, so many, so very big CV. Okay, Professor Natasha, please present the finding hidden pattern in data or how to find the hammer to your nail, a collaboration between human and machine. You have also 30 minutes from now to
Thank you.
12. Yeah, okay, please.
Thank you, Professor Imam Robandi. I'll share my screen. Yes, I hope this will work. I think you're seeing my screen now. Is that correct? I think so, right? Okay, thank you very much. So I'm very happy to be here, even though it's virtual. I wish I could be in Surabaya, but we have to do it like this right now. So maybe sometime I will be able to visit. So my presentation will be a bit more about ideas and how I approach my research. So I will give you some examples, but before doing that, I will introduce the topic to you. So what we are all very good at is finding hidden patterns in data. I think this particular example may be familiar to you. It's a dog in the shades, and I think everybody can see it, right? But what is very difficult for a computer is actually to see the dog here. So they're not very good at finding this particular pattern in this set of data. If we look at this example, this is actually, I'm here in this particular crowd at the Red Hat Days in a city in the Netherlands several years ago. And I think for you, it would be very difficult to pick me out of this crowd. But for a computer who would be fed with my image, it would actually be quite easy and they would be able to find me here. So what I mean to say with these two examples is that sometimes humans are good at doing something and sometimes a computer is much better at doing something. But the best of both worlds, I think, should be used in practice. So we should look at collaborations between humans and machines. So, for example, in my line of work, what you could do in such a collaboration is you have a computer first do the data pre-processing and data visualization. Then you could actually have a human evaluate that visualization to see if there are outliers and whether they should be removed. And then you could continue with computerized data processing again. Or, for instance, in my field of neurology, so that's within the hospital, where, of course, doctors have to do a lot of diagnosis. What we could do is have a machine help us do that. And that could be done, for instance, by first having humans assess the diagnosis to train a machine. Then we can do the data pre-processing. We can do knowledge-based using the knowledge of humans and statistical feature calculation, and then use that in a supervised machine learning algorithm to help the doctor find the diagnosis in the end. So that's also, both of them are examples of how humans and machines can work together. Now, I mentioned things like data pre-processing, data analysis, feature calculation, and it sounds very easy. But the trick, of course, is how to do that, which methods to use. So that is why I had this subtitle to my talk, how to find the hammer to your nail, because you don't want to use a hammer to fix a screw, right? You want to have the right data analysis tool to your problem. So how do we do that? And that is what the remainder of my talk will be about. I will give some general ideas for that, but also give you some examples of my own research. So first I will talk about this general idea. Then I'll talk a bit about the hammers that we have at our disposal. So what is, generally speaking, in our toolbox? And then I will give you two sets of examples. And I'm pretty sure it will all be within 30 minutes. Two about data visualization and data mining, and two about data classification and prediction. So this general idea, how do we get from our nail to our hammer? So from our problem to the data analysis tool that we want to use to deal with that problem. Well, the first point is, of course, that we really have to identify our nail very specifically. So what is our research question? What do we want to know? And then can we give more specifics about that nail? So what are the variables of interest? What are we looking at? Do we know something about these variables already? So do we know something about the expected relations between those variables from prior knowledge, from literature? Or what is very important, if we visualize the data that we have at hand, does it give us clues at which methods would be useful for solving our problem? So then we can choose the best hammer to hit our nail, or in other words, we can determine the most suited mathematical tool or algorithm. Well, the hammers or algorithms are math tools. And of course, all of you know, because I assume most of you are engineers, what an algorithm is. But basically, it's just a step-by-step recipe to solve a problem. So algorithms are like real recipes to cook something. But it could also be what you need to do if your lamp is broken, or if you want to determine whether an email address is correct. All these problems can be solved step by step, and that is what an algorithm does. So actually, if we have our problems, we have different classes of algorithms that we could use to solve those problems. And actually, all algorithms can be divided into these 4 categories or combinations of them. So if you look at this set, so for instance, if you're trying to find the fastest route to get somewhere or what chess move to do next, you're actually looking at a prioritization problem. If you want to find out, like my colleagues want to do, what kind of diagnosis a patient has, or Facebook wants to show you certain adverts, then we're dealing with a classification problem. If you're looking at speech recognition, or more generally separating signal from noise, you're looking at a filtering problem. Or even to mention yet another website, if you're on Amazon, the product recommendation is an example of an association problem. Of course, it's not always as simple that you need only one of these tools or categories of tools. It can also be combinations of these tools that will make up the algorithm that you need. So vice versa, what kind of algorithms are in these categories? Well, if you think of prioritization, you're talking about search algorithms, for example. If you're talking about classification, it could be principal component analysis to do dimensionality reduction, and all kinds of machine learning classification algorithms like random forest, decision tree, support vector machine, and there are many others. If you're thinking about filtering, you're thinking, for instance, about Fourier analysis, which is really at the basis of a lot of filtering methods, or independent component analysis, which can also help you separate signal from noise. And for association, we look at correlation or regression. So by this, I've given you sort of an idea of what is in the toolbox that we can work with. Now, all these algorithms consist of mathematical operations. They're basic mathematical operations that really build up all the algorithms, like addition, subtraction, multiplication and division, exponentiation, logarithms, and trigonometry. And if you combine these basic operations, you can get much more complicated algorithms. The previous speaker showed a lot of algorithms basically, and there was also differentiation in there. And you can make integration if you want to look at volumes or surface or work or effort. Fourier transform, very useful to analyze fluctuations or frequencies in problems. Factorization to provide summaries of data, fitting, and you can go on and on and on. So I've sketched what kind of algorithms we have in our toolbox, right? So let's look at some of the examples now. So the first 2 examples are from my research regarding data visualization and data mining. So this is one of my previous PhD students, Venustiano Soancato Aguilar. And the problem that he was working on, or the nail, let's say, is how to automatically quantify balance during gameplay to adapt the game difficulty according to the skills of the player. So people were doing a game which on a computer game in which they had to pretend to be skating, and by moving their balance from left to right, they could progress in the game. And you want to give them feedback. So how is that done? Well, first we explore more what the problem is. So what we did here is we used multidimensional exploratory data analysis using different visualization techniques, and we'll give the examples in a bit, to find useful measures for quantifying balance in real time. So that means if you want to do that in real time, that it has to be fast. And the assumption that we used in analyzing this problem was that useful measures would distinguish between old and young players, assuming that older players had less balance than younger players. So to be able to solve this problem, what kind of hammers can we use? What kind of algorithms? Well, the measures have to be calculated within milliseconds, and they must reflect the variability of smoothness or speed of the player. So we'll look at different visualizations like heat maps and violin plots. To sketch the problem a bit more in detail, if you look at balance measurements, typically force plate data are used. So people are standing on a force plate, and by keeping their balance, you see how they move their center of pressure, both in an anterior-posterior direction and in a medial-lateral direction, so from left to right or from front to back. And you can plot that in these two ways. So here you see these two axes of in which you can move plotted against each other on the left. And on the right, you see the data from each of these axes as a function of time. Well, this is quite nice to look at balance, but if we want to compare these older and younger participants to find good measures of balance, we would have to plot maybe 40 or so of these figures, and that would be very confusing. So that's not the best way to approach this problem. One alternative way to do it is to use a heat map. So here we have the data from all our participants, so about 40 participants. And from left to right, they're ordered by age. So on the far left are the youngest participants, and on the far right are the oldest participants. And on the vertical axis, you see how they perform over time, and each participant had 10 trials. So you see 10 vertical lines for each participant. Just looking at this graph, you already see a difference between the left part and the right part. So the younger participants, you see brighter colors than for the older participants. So this visualization already gives you some insight that there are indeed differences in how these younger and older participants behave. And we can already derive some features that might tell us something about how these participants keep their balance. Let's look at a different visualization to get into that. This is the same data, but visualized in a different way. So now horizontally, we have again the participants ordered by age. And these are so-called violin plots. So per participant, we now have the distribution of the data, and the axis, the left-right axis of their movement is displayed vertically. So you see these two blobs for every participant, and that means that they spend most of their time either on the far left or on the far right, and they spend less time going from left to right, and that is the small part in the middle. You also see that if you compare the younger participants on the left and the older participants on the right again, that the extent of movement is larger in the younger participants, and they spend less time going from left to right. They spend less time in the middle. You see that the reddish colored violin plots are a bit broader in the middle. Also, you see that the almost oldest participant, who's 78 years old, so who's almost on the far right, has a slightly different visualization. He or she spent much more time in the middle, so that participant was not moving that much. So this visualization also gives you some information about what's happening. Now, what we did in the next phase is that we actually derived different types of movement features from the trajectories of these participants in the force plate data. So now we again have horizontally the different participants, but vertically each row indicates one of these features. So we already derived measures from the data. And these measures are things like curvature of the data, turbulence intensity, covariance, root mean square, standard deviation, and rough speed. So they all tell something about what's going on in this movement trajectory. And then again, you can see that, for instance, the top 3 rows that have to do with curvature and turbulence intensity, they do show a difference in intensity between the younger and the older participants. So these are candidate features to use to give feedback to the participants about their behavior during this game. Similarly, we see that for the root mean square and a little bit for the speed which is in the lowest row. Yet another way to see which features would be most promising to use to give feedback to the participants about their behavior is to have the violin plots of the distributions over all participants overlap. And then you expect that those features that are most different between the two groups of participants would be most useful for a problem. So here the different features are ordered from left to right, and then on the left are the ones that are most different, who have less overlap in their distributions. And to the right, you see that the distributions overlap largely, so they would not be very informative to give participants feedback. And on the left, we now have the root mean square and the turbulence intensity and the curvature again. So in a slightly different way, we again arrive at similar features to be used for a problem. And then this is yet another visualization of the same data. Here we do data reduction. We use a principal component analysis of all the data that we have. And the data are plotted here against the first two principal components. So the first principal component is on the horizontal axis and the second one on the vertical axis. And together, these two principal components explain about 80% of the variance in the data. And then what you see, if we have color-coded the younger and older participants again. Older participants are pinkish and younger participants are bluish. And you see that some of these variables that have been projected on this plot are really good at distinguishing younger and older participants. Those are the variables that are aligned with the vertical axis or almost aligned. So again, the root mean square and the covariance, for example. I'll skip the right plot. So yeah, to conclude this example, from these different types of visualizations, we can conclude that some of these variables will be good at, that are good at distinguishing between older and younger participants, can be used for giving feedback about balance performance to these participants. And all features or parameters that you see here were calculated from a small amount of data points. So you can use them to do this real time. They don't take a lot of time to calculate. So that was the first example. The second example I will not go in detail in. I recorded this presentation and it will be online later. And you can look at this detail in this example in detail later on. But I wanted to mention it because it's a different type of data. So we also derived a way to visualize multi-channel EEG coherence networks. So EEG is a way to measure brain activity, electroencephalography, and coherence networks tell you something about how the brain is collaborating, so how different brain areas work together. And the problem is if you have a lot of these EEG channels on the head and you want to calculate all these different coherences and you visualize those, then it's going to be a clutter. It's not really easy to see. So in a similar approach, we tried to derive a data-driven way to display this information without making it too cluttered. So that you can look up yourself. I'm sorry that I don't have the time to go into detail here, but I wanted to share two other examples with you from the data classification and prediction part. So this is Octavio. He was also one of my former PhD students. And one of the problems that he worked on is that in practice, when my colleagues are assessing patients with Parkinson's disease, they are not always very consistent at that. So the so-called low, the inter-rater reliability is rather low. What they do is they look, for instance, at how fast these patients move. And it's typical for Parkinson patients to move slowly, and that is called bradykinesia. And this is assessed by just looking at the patient's move and giving a clinical score for that. So what we wanted to solve for our clinician colleagues is how this assessment of bradykinesia can be done more accurately with higher reproducibility. So what we did is we measured the movement using inertial measurement units and then predict the bradykinesia score on a continuous scale using features derived from those movement parameters. I will show you how this is done in a bit. And for that, we use different tools, different hammers from our mathematical toolbox. We use backward linear regression. And for the prediction to see how well it worked, we used leave one out cross-validation. So let's see how that is done. So here we have on the hand a small IMU, inertial measurement unit, that contains accelerometers, magnetometers, and gyroscopes. And there are different ways to combine the measurements from such a unit into or to get a three-dimensional movement trajectory. And that's called sensor fusion algorithm. From that sensor fusion algorithm, you get so-called Euler angles. And from that, we can derive features. So features that are related to the type of movement. And we derived those ones that we expected to be useful. So I'll show you what that was done. Of course, we have here our algorithm. So this is an example of what the data will look like if the patients are asked to do finger tapping. So in finger tapping, you have to move your hand like this as fast as you can. And the movement is then a bit sinusoidal in one of the main Euler angles. So that you see here. Now, features that doctors look at is how fast the movement is, whether it's regular, so if it's a regular frequency, whether the amplitude is changing and things like that. So we used similar ideas to derive the features from this Euler angle. We used both the raw signal as well as the spline fitted signal, so the smoothed signal. Then if you do that and you have this whole set of features, you can predict the score that was first given by clinical evaluators using these features as predictors in a linear model. So we used, in this case, backward stepwise linear regression. I will not go into the details, but again, here we have an algorithm, of course. So what you then do is you first use the data to build your prediction model. So you have the patient movements, you derive these features, these movement characteristics. We use the linear regression model to predict the patient scores given by our clinicians. And then we have our prediction model. But now to see how that model would do on new data, we use leave one out cross-validation. So in the lower row, you see what is done then. You take out the data from one patient, you train your model on the remaining data, and then you see how well this model predicts this one patient characteristics that you took out. This is also an algorithm. So this is what we got in the end. This is just one example of one patient left out. So here the red example was left out. On the horizontal axis, you see the clinical scores. On the vertical axis, you see the scores predicted by the model. You see for this particular patient who was left out for this run, the prediction was not very good. So we had a test error of a little bit more than 1. And you see the orange line is the particular model with this sample left out. And the blue lines are the models created in each leave one out cross-validation step. But if we do this for all the patients that we have, we find that the cross-validation error is 0.38, whereas the difference in assessment between all the clinical evaluators is 0.57. So the model actually does a bit better than the clinicians do. I think I have a little time for my last example. I'm looking at the chair. Is that true?
7 minutes.
Okay, that will do. I'm happy that I can give you my last example. So this is yet another PhD student from our group, Gerrit Kramer, and he worked on a slightly different problem. We see many patients with movement disorders in our department, and one of the symptoms that a patient can suffer from is tremor. Tremor is basically a trembling movement. Can be in the hand, can be anywhere else in the body. Now, this tremor can have an origin really in the body, let's say an organic origin, or we cannot find that organic origin, and then it's called a functional tremor. These type of tremors are difficult to distinguish. So also here, we try to make that easier for the clinicians by measuring the movement and then using a method to analyze these tremor data that is independent of what the patient was doing exactly. And the idea that we used is that we know that for the functional tremors, the generator of the tremor is more unstable than for the other types of tremors. So what tool did we use here? That was wavelet coherence analysis. So let's have a look at that a bit more detail. I don't know if everyone knows what coherence is, but the simplest way to say it, it's correlation in the frequency domain. So it will give you a coupling measure between two signals in terms of frequency. It varies between 0 and 1. 1 being a very high coherence, suggesting a common drive to the muscles involved in this particular movement, and also a central generator. Now, normal coherence analysis is like Fourier analysis. You need more time to have a reliable estimate. So that is not very suited if we want to look at the variability over time in this measure. However, we can do that if we use wavelet coherence analysis, because wavelets can capture changes in frequency over time. And that would be particularly suited to look at this functional tremor, because we know that it's less regular, that it has frequent interruptions, irregularities, and frequency changes. So this might be a good tool to hit this particular nail, a good hammer to hit this particular nail. So we looked at quite a large group of patients, almost 100, who had different types of tremor. Most of the tremors are organic. So Parkinson tremor, essential tremor, and enhanced physiological tremor are all organic. And then we had a group of functional tremors. And they performed some movements, and we analyzed the data if we had at least 20 seconds of tremor during the same posture, but they could be different postures. So here's an example of a visualization of a functional tremor on the left and a Parkinsonian tremor, which is an organic tremor, on the right. And on the top, you see two EMG channels. So they measure muscle activity, then the accelerometer signal. Below that, the coherence signal and the phase diagram belonging to the coherence, and the wavelet coherence analysis in the colorful plot. So the wavelet coherence shows horizontally time, and on the vertical axis scale, which is a measure of frequency. And you see clearly in these examples that the functional tremor has these irregularities that we want to capture, whereas the Parkinsonian tremor is much more stable and also shows a more continuous high coherence over time and also consistent phase. So which features could we extract from these signals that might be relevant? I won't go into detail to all of them, but what we looked at, for instance, was the percentage of time the tremor was active in both EMG signals, was present, the percentage of time that we had significant wavelet coherence, the number of valleys, you could say, so the number of interruptions in the wavelet coherence, and some other measures. Then what was done is use a decision tree approach to distinguish between these two different types of tremors. And what you see in this graph, which represents sensitivity against specificity, where sensitivity means how well are we able to capture the functional tremors, and specificity, how well are we able to capture the organic tremors. In a perfect case, we want to have this line go to the upper left corner. So the closer we are to the upper left corner, the better the performance of the method is. And you see that the dashed line with the little dashes is the wavelet coherence analysis that outperforms the standard coherence analysis to make this distinction. So what decision tree do we end up with then? What we did also is we had two different approaches. First, we only looked at the periods that tremor was present. So that is what is called the tremor detector here. So by starting to look at the number of valleys, so the number of dips in the wavelet coherence, when you look only at the periods of tremor, you can already distinguish part of the organic tremors. Then in the next step, you look at the percentage of tremor, percentage of time with significant coherence, again, using this tremor detector. And then you split out more functional and organic tremors. And using this approach with basically only two features, we can almost classify 84% of our tremors. So that is pretty nice. It's a pretty good performance that might be helpful for clinical practice. This was the last example that I wanted to give, and I thank you for your attention. Please look up my my research on the two websites below, and I'm always happy to answer questions later or now. Thank you.
Okay, thank you, Professor Natasha. So we have 15 minutes for question and answering. So you can use the raise hand, also the chatting. Also, maybe there is some question from YouTube. Okay, is anyone want to ask?
Prof. Imam.
Dr. Ketut Edi Purnama, please.
Thank you
Nice
very
to
much,
see you
Prof.
again.
Imam.
Professor Natasha, he is the dean of our faculty. Dr. Ketut.
Yes, we have met in the past. Nice to see you.
Oh yeah, okay.
Natasha, hoe gaat het met you?
Het gaat goed, dankjewel.
So
Okay,
you can use the Dutch.
only that sentences. Okay.
Goedemorgen.
Goedemorgen. It's been a long time. I don't see you, Professor. So I remember that when I was a PhD student in Groningen, once I have visited your lab about using your magnetic tracking system. Yeah, you still remember that you have sophisticated equipment, and I use it for my research related to ultrasound. My question right now, because currently I also doing research in brain disorder, but not in signal processing. We do in MRI image analysis to detect brain disorder. So related to your research, how far the relation between the signal and the image in the brain disorder, for example, in tumor or in Alzheimer and so on. Thank you very much, Prof. Natasha. Very nice presentation of you.
Thank you.
Okay.
So let me repeat the question if I'm not entirely sure what you're asking. You're asking how sensitive the brain signal is to detect the disease, or?
Yeah, maybe the relation or the combination between image and signal of the brains can can raise this the accuracy or sensitivity. Thank you.
I see. Yes. Okay, that's very interesting. In principle, the more methods you combine, the more information you get, of course, right? Especially if the variance in the data that is explained doesn't overlap. So, for instance, if you're looking at functional data, which is more my field, then we do combine, for instance, fMRI and EEG or EMG. Because we get different types of information. So fMRI, for instance, is very good at spatial localization of where something goes wrong. And EEG or EMG is much better at finding when things go wrong, right? It has a very good temporal resolution, but not so much a good spatial resolution. So besides finding the right hammer to your nail, you should also combine them in the right way, of course. So I think if you find the best of both worlds, it is, of course, very beneficial to combine methods. Yes.
Is it on your research direction also to combine the image?
We do combine images as such a little bit, but we use more the functional data. So we're looking also, for instance, now at functional near-infrared spectroscopy, which is a bit more useful in clinical practice than fMRI. So we do look at these combinations, but I myself do not look so much at only the images. So I don't look at the structural data so much. I look more at functional data.
Okay. Thank you very much, but still open the discussion related to
of course.
the brains. Thank you very much.
Okay, maybe another questions from the participants. You can present or directly. Yes, yes.
I have one question.
Oh,
Padi.
Okay, please. Oh, okay, Dr. Adi.
Natasha, that was a nice presentation. So I would like to focus on the discussions of coherence.
So, excuse me, you better you introduce yourself from where and who are you?
He's the student of Natasha.
Professor Natasha. Ik ben van Surabaya, ik ben oud van Surabaya en ik heb 4 jaren daar in Groningen voor studeren. En hier we hebben heel veel of mijn collega in ITS. So it's a short introduction that for Professor Imam Robandi. So I'm a lecturer in ITS in the Department of Computer Engineering, and Mr. Ketut is our dean now. And I have one question regarding your last example in your case of study when it discussed about the coherence in EMG data, Natasha. I was wondering if you try to calculate the coherence informations from the same persons and from the same muscles, will it be reach the 100% coherence?
Well, it will not reach 100% coherence, but depending on the coupling between those muscles, it can be very high, of course. The reason why we actually did calculate coherence, that was also in the receiver operating curve that I showed, but it's less suited because it doesn't capture the fluctuation so much over time. Coherence will only give you an average assessment over time. That's just inherent to the method. So you can do it, but it's less suited to make this distinction between different types of tremors.
Okay, yes. The second question would be about hammer and nails, Professor Imam.
Yeah. So many identities very confused with the term hammer and nail.
Yeah, back to hammer and nails. Some visualization is one of tools to visualize our data, but sometimes it is a bit subjective. For example, if we think this way is simple and how to call it, it can visualize better to our mind, to our thinking, but sometimes it is too complex for others, or maybe vice versa. Sometimes it is complicated for us to represent the data. So then we choose the simple way, but it is difficult for audience to understand the logic behind this algorithm. So there is some kind of a trade-off in these situations. And if the algorithm that we choose is a bit complex, sometimes we have also difficulties in explaining in the paper, because then it's not an easy task. So
enough. Yes.
What's the question?
So what is the best practice that you usually choose for solving this such dilemma?
Yeah, I think you're completely right. It's not that there's one tool that fits all, right? There's not one hammer that always hits the nail. That's the whole point of this presentation. And I think both the signal analysis and the visualization should go hand in hand. And sometimes you use one first and then the other. But what I always tell my PhD students, for instance, is that doing statistics as such is not worth anything without visualization. Because the statistics can give you all kinds of conclusions. And if you do not look at the data first, then you don't actually know what you concluded. So for me, it's sort of a natural interplay between the two types of approaches. And I think I tried with this presentation to give sort of a manual on how to approach this. But of course, it also comes with expertise, right? The more you do it, the more feeling you get on when to use the visualization and when to use the signal analysis methods. But I hope with this presentation, I've given you some examples of how these two could go hand in hand.
Thank you.
Okay, thank you. Okay, this is the first time for me to heard about a hammer and nail. Okay,
I hope you will never
yes,
forget.
Yes, because my background is power engineering, so very far away with the hammer and nail.
Yeah,
Okay,
yeah.
Professor Natasha. Maybe we have another question from YouTube. Dr. Vita want to explain about the question from YouTube?
Yes, Professor Natasha, I actually have several questions here. I think it's okay if I try to combine this question that are sent to me.
No. This is their question or another question from YouTube.
From YouTube. So, the team has sent me several questions. So I would like to combine this. As for this, okay, so this is from Kairul Nisa and Rahmat Febrianto. We are having this COVID-19 situation right now. So have you any real case experience implemented using or examples of this hammer and nails related to COVID-19? And another question is it possible that artificial intelligence can help scientists in making or inventing medicine? Yeah, I hope
Nice questions. Yeah. Let me say beforehand, I'm always happy to answer questions also after this conference, right? So if the organizers can email me some questions, I would be happy to try and answer some more questions. In my presentation, I gave a few examples, but limited about how we can use machine learning or AI approaches to help our clinicians do their tasks. I haven't, to go back to the first question about whether I've been involved in any COVID-19 research, I haven't personally. So also in our hospital, of course, many people are looking into this. We've been fortunate in our part of the Netherlands that we didn't have so many cases. So that's good for us. That's bad for research because it means that you cannot learn so much from these cases. But we are collaborating with our hospital in multi-center studies and doing our parts. We are looking more at the impact of the quarantine regulations on what happens to people. So not only the disease itself, but also the consequences of how to deal with that. But again, that's not my personal experience. As far as machine learning is concerned, I find that a very interesting development of recent years, of course, to make the step now to clinical practice. What I have found is that there are a few difficulties in, at least in neurology, compared to some other fields. So far, machine learning in medicine has been very influential, I think, in imaging, in radiology, for instance. But for neurology, it's a bit more difficult. One thing is you need to have enough cases. And even though we have a lot of Parkinson patients, for instance, in the world, it's still difficult to get all this information together. And the other thing is that if you want to use classification approaches, you need to have a good label, a good gold standard of assessment. And in many cases, diagnosis remains a bit uncertain, sometimes even up to death. So we have to work with, let's say, more a brass standard than a gold standard sometimes for clinical applications. So I do think machine learning is very promising also for clinical applications, but we also need to think about these particular problems that we have in clinical applications.
Okay, thank you very much, Professor Natasha. The time now is, just have 2 minutes maybe. Another questions?
There is actually a question in the chat feature, Prof. Imam. Would you like to read it? Oh, sorry. Let me.
In chat. There is
I see also that someone asked if my email address can be shared. Yes, of course. It's also online. So, yeah.
Okay, thank you. Yeah.
Okay. Do we have time for one more question? Or
I think so.
Or maybe, I don't know. Or
Yeah,
maybe we can.
we don't have enough time now,
Yes.
so.
So yeah, so I think the participants can send the question directly to Professor Natasha's email.
That's fine. Yes. It was a
Okay.
pleasure participating. Thank you.
Okay, thank you, Professor Natasha. And we get applause together for Professor Natasha. Yeah, that is the virtual applause. Okay, thank you. For the next our presentation, so the time for Dr. Ardyono Priyadi discuss about the transient stability analysis for obtaining the critical clearing time and setting of the relay protection based on the critical trajectory and time domain simulation method, of course, in the power system. Yeah. So before that, I would like to read the curriculum vitae, the biograph. The Ardyono Priyadi received the bachelor degree from ITS in electrical engineering. So he was my student in the past time. Yeah. In power engineering in 1997. He received the master degree from Hiroshima University, also the doctor degree in electrical engineering from Hiroshima University. So he can speak Japanese very well. Yeah, not Japanese, Japanese. Yeah, in 2008 and 2011. So he was the formerly head of the electrical engineering department in ITS. And now he is a deputy education of the graduate and provision in ITS. So this is the achievement. He received the best young researcher ITS in 2000 and best accomplished lecturer ITS in 2017. The research interest is power system, transient, and dynamic stability, renewable energy, smart grids, and identification of the power system. Dr. Ardyono, you have 30 minutes, please.
Thank
Not
you.
more.
Okay. Okay, I will share my presentation. Okay. Okay. I hope everybody can see my presentation. Is it all right?
Yes.
Yes. Yes. Yes.
Okay. 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 Good afternoon, everybody. So I present about my research topic, which transient stability analysis for obtaining critical clearing time and setting of relay protection based on critical trajectory and time domain simulation method. This one is the list of content, our presentation, introduction. This is about the critical trajectory, obtaining critical clearing time using a critical generator and losing synchronism based on critical trajectory, then a simulation result, and for interesting part is I will share also the transient stability application, then the conclusion. Then what's about the introduction? So in the power system, published by IEEE in 2004. So the power system is power system stability is divided by three. There's a rotor angle stability, frequency stability, and voltage stability. So in here if we focuses in the rotor angle stability, so there is a small signal stability and transient stability, but maybe we in here we doesn't see about the steady state stability. So if I can improve it this part, so the steady state stability actually is in the small signal stability, but in the actually we can also found the steady state stability using voltage stability. It's mean when the voltage is collapsed, so rotor angle is also collapsed. This one is because of that there is a relation between the steady state stability and voltage stability. So the method of using for transient stability analysis, we can divide it become two. One is for single machine system, the other one is for multi-machine system. For the single machine system, we know about the time domain simulation or TDS or numerical simulation method. Then energy function, that's one is equal area criterion, and then critical trajectory. So for multi-machine system, we can divide it become two. One is a non-direct method. It's mean we cannot find the CCT directly. This one is TDS. The other one is a direct method. This one is energy function, critical trajectory, and artificial intelligence. So in here in about the critical trajectory, so there are three kind of part of the reset of critical trajectory. So but in here, I just focuses about the critical generator and losing synchronization. So for procedure for transient stability, so in the transient stability, so we should have the three kind of configuration. First is the pre-fault configuration, and then on-fault configuration, and then post-fault configuration. So exactly, so for the analysis of about the stability and transient stability, so we always use it the for example is a rotor angle between the time or speed generator with the time. So the rotor angle increases due to the excessive kinetic energy is not absorbed by electrical load after the fault. This results in large rotor angle difference, which involves along the time. This system is considered to be unstable, but sometimes it is very difficult to obtain this one is to just this one is stable or not. Because of that, I will explain it our proposed method to obtain the most simple way to justify this one is stable or not. So this one is I propose the critical trajectory. So in the critical trajectory method, we use the omega and delta. So in here, there is part we call the SEP, stable equilibrium point. This one is unstable equilibrium point or UEP. So I will discuss further about the SEP and UEP in the next slide. So in here, the trajectory itself, this one is the fallout trajectory. Then number two is the trajectory will go to the stable, always stable. Then number four is the trajectory will go to the other point of stability. It means it's not stable. Then number C is critical trajectory itself. The critical trajectory, it means the trajectory start from on fault, then can move to the read can the UEP and the single machine infinite path system. But in the multi-machine system, we cannot show about the UEP. So I will discuss further about that UEP and the multi-machine system. So it's mean if we using time domain simulation, so all need be trajectory will move part from critical trajectory. Why the condition is like that? We'll discuss also in the next slide. So it's mean the conventional numerical integration method fail to read the UEP. So in the single generator to infinite path, this one the nomenclature. So in here, so this point is losing synchronism. So I will propose for transient stability. Will I discuss later also about that. So in here, so there is a SEP and UEP. Then if we model by the simple way the swing equation, then we can analyze the swing equation is become like this. Then using the state space, so we can analyze the metric A. From this point, we can find the UEP and SEP. So if we found by the eigenvalue, so and the SEP, the real part always negative. It means this condition is always stable. Because of that, we call the SEP. So, but in the UEP, but this one, the couple of the eigenvalue, one is negative, the other one is positive. It means the value is put that is one is the condition is sometimes stable and sometimes unstable. Because of that, we call the unstable equilibrium point. So if we analysis further about this condition using the right eigenvector and the left eigenvector, so we can find the eigenvector first for eigenvalue first, then eigenvalue second. Then if we draw it, so this one is mean the critical trajectory. So the critical trajectory implies is like the asymptote. Because of that, we cannot find by the time. Yeah. Because of that, now we propose how to solve the critical trajectory about the asymptote using the easy way. Then we can find how to critical trajectory. Then together with critical trajectory, we can find the CCT. So now we discuss about the obtaining CCT using the generator, critical generator, and losing synchronism. This one is the concept of the critical trajectory based trapezoidal method. It's mean, so, and if we using the trapezoidal theory, in this one is time. So if we calculate this time, the trajectory instead, we cannot find it. Because of that, we should move path to change from time become the distance. So this one is the distance. To solve the distance, so we use the Newton Raphson. But the Newton Raphson, this one we know, this one just the we found the point. How to calibrate the point is become line. So it is a easy way. So we can using the minimizing problem. Then we found it simultaneously. So we can find the line itself. So it's been this one, the step with sim distance, of course, we can distance, then two boundary condition. So in the integration theory, so we can use the initial value. The other one is boundary condition. So in here, we using technique of the boundary condition. This one is the x0, then the other one is xm plus 1. This one we call the CP. Why CP? Because we propose this one. The CP is there is the using the UEP. The other one is CPS using losing synchronism. Okay, so now how to get the numerical integration from distance from time to become distance. So this one is the time. Then we change the become the system is like this. Okay, this one is the endpoint condition critical generator. So I call this one method as P to make the simple thing. So for method B, so the critical trajectory CUEP in this SMIP system implying is xm plus 1 is equal xu. So this one is assume that only the critical generator can reach the UEP. So it's mean we should make the procedure. So because maybe there is not one generator, we have 2, 3, 4 more or 100 generators. So only one generator, that's one the critical generator is can reach the UEP. So using the weighting matrix, so we can find in the critical generator, that's one. With the critical generator give the first one value, then the other is small value. Using this method also, we can modify this method B. If we modify this method B, so because only one generator, this one is the critical generator, is can read the CUEP. The equation is always the same, but the number of equation is different. Because of that, if we modify the method P, so become the number of equation and the number of the parameter, that one is the sim. Because of that, we call also method to modify the method P become the simultaneous equation. Then and here also we propose how to select a critical generator, so we can use the energy potential index. So this one, the potential energy index, I have proposed, and then I have published it in the IEEE. Then using formulation method P, so with some minimization, so the system of sample is like this. Then the trapezoidal theory, from time to become the distance. Then the boundary condition, there is the initial condition, the other one is the endpoint condition. So the different method P and method B modified, I already said in the previous slide. This one is just the number of equation and the number of parameter is different. So to solve this, so M is specified to obtain X or and tau. Then CCT is obtained by solution of tau. Then the Newton-Raphson method for solving the optimality condition. Okay. Then endpoint condition for losing synchronism. Then for simple way, I call method A. So in the synchronizing power matrix is singular if delta PM plus 1 for delta theta, so it's become 0. This one is the term of synchronization. So if the losing synchronism, so we can check also the eigenvector, that eigenvector should agree with direction of the CUEP. Because of that, we can find the vector itself. So because of that, the endpoint condition we can find is become like this. This one is the condition of the delta. Then this one is the direction of the trajectory. But also in the method A, we can modify it. If the vector is 1, of course, we agree with the vector is always agree with UEP. It's mean the KS is become 1. It's mean we can modify this like this. So because KS is become 1, so the delta PM for delta PM multiplied by delta PM dot is equal 0. So this one is more simple than previous analysis. Then for formulation method, so the whole system is the same, but the difference is method A and the method B is the heart of to find the endpoint condition. So because the endpoint condition is different, so the result is rather different. Okay, this one is for modify. Then the simulation result. So I tried the simulation and the point G for IEJ West machine 150 bus system. Using the X prime model is like that. So in here I use the PC center of angle. Why we using this one? So it's mean if we using center of angle, it means the reference and reference machine is together. So not only one machine to become reference, but the reference machine is together. So because of that, now using this equation to find the CCT or sometime else. Then the result shows like this. So yeah, with the minimum error. So our method E and method B can find direct CCT directly with a small error, or we can see accepted error. With compare with simulation method and scheduling method. So this one is by figure. So the difference method A and B is can very clear in here. So if we found the using method P, so endpoint condition is CUEP. I already talked in the last slide. So there is difference with the UEP and in the single machine and the multi-machine. In the single machine, of course, we find exactly we can find the UEP, but in the multi-machine system, it is very difficult to find the UEP. Because of that, yeah, we agree. We agree actually. Call this one is not UEP, but controlling UEP. So this one is not exactly UEP, but we can found this one has become controlling UEP or CUEP. But if you use method A, because the endpoint condition is the losing synchronization, just before several point before CUEP. This one the different method A and method B. So in the more complex analysis, so we can analyze this. Of course, the method A, method B can follow the time domain simulation. Is of course can found the CCT also. Then how about the and the controller? It's been in here. I put the more previously without the governor and AVR, automatic voltage regulator, but now we put the automatic voltage governor and automatic voltage regulator. So the difference is this one. So there is a control with this one. So I just put the simple control this one. How to different to find the effectiveness, and our method can find the CCT. So exactly. So we can find the CCT. So this one is using time domain simulation. This one is in the critical time is 0.294. Then this one is 0.295. So CCT is between that one. Okay, this one is in the critical trajectory for critical generator also for many generators. So we can follow the time domain simulation also. This one is in the critical trajectory. So we can find also the CCT also. So finally, so in the using the controller also we can find the accept the value for CCT. Then now more interesting part, how to use the transient stability application in the, for example, in the industrial application. So now we already use the transient stability in the small part in the laboratory. So using the WAM, so it means as width area measurement. So just which means a monitoring by a load, then we change using analysis, transient stability analysis, then the CCTS will change it. This was a monitored online like this. Then the final destination is for security and resiliency of smart grid. So now our research is also using the SGS, but I'm sorry, I cannot share the SGS now, but because now it's become research, then we found some certain part, then we will publish it in the journal. I'm sorry. Okay. This one is the third generation our module, how to monitor the transient stability, because we try to make the cloud computing. So we move part from this part become this, but this one is still developing. But now this one is already published, then try to patent. The other one, how to make the setting relay in the FB found the CCT. Okay, for example, it's like this. So for example, when the CP3, the setting is 0.1, the CP2 is 0.3, the setting CP1 is 0.5. Of course, this was coordinated well, but the problem when short circuit in here, so the CP will clear 0.5 plus if this one is in the normal way plus 0.5 12 second. It's been a 0.62 second. So already the generator is already collapsed. Yeah, in our transient stability researcher, so we worry about the generator itself. So it's means the generator will clear by relay already late. So maybe the generator will broken. Using the sophisticated setting, for example, it's like this, sophisticated setting, or we can create the unconventional curve. Now we because now and there is some relay already have the sophisticated setting. This one, for example, if we can setting in here, so there are two kind definite time, so we can save the generator. Why? Because the short circuit current when occur in here and occur in here is different. Because of that, we can use the sophisticated setting. But if the current is the same, of course, we cannot use this setting. So maybe we can create the other curve. For example, the unconventional curve. The other one, to solve this one, using differential relay at bus 1. Of course, this one is more expensive, but this one can solve the problem also. The other one, or we can install the SCHES. Okay, but we can discuss later because I cannot share about the how to just access it because not yet published it. Just still research. Okay. Then this one is the other parts of our research. Then how to make the digital research protection using the artificial intelligence. Why this one? So the important thing first, this one can improve numerical relay performance. The other one, the second, adaptive relay for operation and security of smart grid. Then the most relationship with the transient stability analysis is unconventional curve for considering transient stability assurance. I already thought in the previous slide that if we use the sophisticated testing, we cannot solve it. We can use the unconventional curve. Okay, then this one is the most parts I like it because this one is have go to patent also, then have published also, then implemented in the industrial way, then and now is established around start from in 2015 and 2016. Yeah. So okay, this one for example, if we have a small system, power system is like this, then it's connected with grid. This is now the new feature. This one is more important thing if we have like this. Of course, the problem is in here. How to make the setting in here? If the short circuit in the spot, of course, this relay, for example, is overcurrent relay, and overload relay, over voltage relay, and the other relay can handle it well. But the problem, if the short circuit in the grid, so in the inside, outside the system, of course, that all the relay cannot handle it. Yeah, for example.
So you have just 4 minutes later.
Okay, thank you. This one is a final slide. Thank you very much. Okay, so if short circuit in here, how to solve it? Yeah, so the important thing to solve it is, yeah, using the directional power relay. Power relay in here is, if we're using the IEEE standard, the number is number 32. How to setting it? The important thing is we should know how the type of the load itself. If the load is steady state load, this one is okay. This one is very easy. We can use the steady state way using the power flow. This one can found it. But if this one is the dynamic load in here, of course, we cannot find it by power flow, because power flow just work in the steady state part. But it's here we should use the transient stability. How to find it, the setting of the power flow. The important thing in here, how to model it, the short circuit in here to become the big value of power will flow in here. This one is a more important thing. So it's been because when short circuit in grid, so all the power in the generator not flow in here, but also flow in the grid. This one the problem. So if we cannot find the setting really in here, it's mean the generator will be collapsed. The system of course will be collapsed. Okay, this one the important thing in here. So how to setting this one? This setting is the procedure of the setting. If you want to know more deeply, because this one is already published in I'm saying journal, so you can download it because open access journal. Then you can read it. If there is any question, you can discuss with us. Then I will send email to you. Okay, so the conclusion, the critical trajectory method based losing synchronism and critical generator provide direct exact CCT with error can be accepted. Now CCT can be improved by SCS. We will discuss later. Monitoring TSA can handle by critical trajectory method. TSA is not only obtain CCT, but it also used for advanced setting relay over current, govern unconventional curve, under voltage relay, export-import relay. Thank you. This one is our member in Instrument Measurement and Power System Identification Lab. We call in Indonesian as LIPIS. This is Professor Harry. This one is my higher member in my lab. This is Dr. Marco. This one my head of laboratory. It's me, member. Then is Dr. Vita, now become the session chair in here. Then the other one is Mr. Samson. Thank you very much for your kind attention.
Okay, thank you so much, Dr. Ardyono. So now we are in the very complicated mindset today. Discuss about the damping from Professor Haiping, discuss about the signals from Professor Natasha, and the last one we discuss about trajectory, stability, dynamic stability, transient stability, and protection. So please you don't ask about what is the relation between trajectory and COVID-19. Yeah. Okay. I give you the session for a question. So please you raise hand or write in the chatting. So maybe this is a very complicated numeric in the presentation. So anyone? There is anyone for question?
May I have a question, Professor Imam?
Which one?
I am Dedet from Electrical Engineering, ITS.
Okay, please you introduce yourself. And
yes, my name is Dedet. I am from Electrical Engineering, ITS. And it's quite interesting following the presentation from Dr. Ardyono. My question is how far actually the simulation or calculation is implemented in the protection setting in large-scale system, for example, in Indonesia, in Jawa, Bali. Because I think the more accurate the data, I think the result will be close to the actual condition in the field. So the question is very simple: how actually this calculation is implemented in the large-scale system in Java and Bali electricity system? Thank you very much.
So I added small. The Jawa Bali electric system is the backbone of Indonesian electricity. Yeah. So Dr. Dedet called as the large system. Okay. The answer from Dr. Ardyono.
Thank you very much for Your question, Mr. Dedet, is my head of department. Okay. Actually, so before we discuss about the Jawa Bali, our system, and about the transient stability step. So when I studied in Japan at that time, I just discussed with the TEPCO energy, and the other one is the Chugoku electric. And that's time how to implement this one in the real system, because if we implemented this one, it's mean, of course, we need the so because this one the calculation time, it should be concerned about the system, and that's time because in that situation there is a professor also from the BC Hydro in Canada in that time. So actually, in the transient stability analysis with in the monitoring system, it's mean actually we can accept it if analysis itself is not should be fast. For example, in the monitoring system, it's mean we can still accept it if the calculation calculation for find the CCT in the in the real situation. That's one is for 5 minutes, for example. So every 5 minutes we can check it. So okay, we can give the the result. This one, or if the weak panel the load is like this, so the system has become like this. So for example, 5 minutes, that one is quite enough time to show to us how the real situation. But I believe with the cloud computing now, maybe the time that one has become very fast, we can do it. But until now, I cannot do it because still going. How to found the data? All the data will go to the cloud. So yeah, maybe in the near future, maybe I can share what the result if we use the cloud computing, how fast and how the accurate about the analysis, our analysis in the real system. The other one actually, the important thing in here is we can find in the real system is how to find the characteristic of the real system is the same as our simulation. This one is most the big problem. So if we have, for example, the such kind of data, so for example, monitoring system, we have it, I believe, so we can make our simulation is maybe near with the real simulation. That's one the way we simulate. If we have the more data in the, we can find in the simulation maybe close to the real situation. Thank you.
Okay, Dr. Ardyono, maybe enough for you. Maybe you can continue your discuss in your laboratory, and you can discuss in the office of the Dr. Dedet. So yeah, so this is opportunity maybe for another people from outside of ITS, maybe want to ask about the transient stability, dynamic stability to Dr. Ardyono. Okay, please.
We have questions from YouTube actually.
Okay, it's from YouTube. What about question?
Yes. Dr. Ardyono, with the penetration of distributed generation or embedded generator in a system, how can the stability of the system be seen? Is it clear?
What the stability of?
With the consideration of distributed generator penetration.
The voice is not so clear.
How is the stability of the system if we consider the penetration of distributed generator?
Okay, Okay, I can catch the answer. Okay, so it's been the penetrated of a distributed generator. This one is first is we should know what the type of the DG itself. So it's mean if the DG is not for example, it's not a generator. It means it's not a conventional generator. Certainly, for example, if we use the other, for example, if we use a PV or something, this one is different because of PV, because there is something as different. So we don't use the. It's mean it's become from DC to AC. It's mean using the for example, using the converter and the system. For example, the situation is like that. So now we try because the problem is inertia. The inertia, if we use the inertia, if we use the PV, it is managed. We will lose some inertia. So because of that, now some researcher in the not in the area, maybe it's like Mr. Dated area in the power electronic, they created how to make the virtual inertia. That one is more important because the virtual inertia, this one can handle. So it means to add the inertia in the system lost by PV of sample. But if we still use the, for example, the GG itself is the conventional generator, of course, we can use it the conventional generator. This one is no problem. But the different view, for example, if we use the like that, different. For example, we have a small grid that connected, the small system that connected to grid. The model is different because there is a big generator in the grid. So it's been everything is depend on the grid. But in such kind of situation like I present before, this one we should consider about the how the short circuit in the grid. But if short circuit inside grid, of course, the stability is very strong enough, very robust. But the problem is short circuit is not in the system, but in the grid. That's one is big problem. Because of that, and now, right now in our experience, then now is already implemented, then so working well in the two industries in Indonesia. That's one is working well. We can do the setting. If the setting really, that's one is clear enough, that's one is can handle it. That's one is maybe the concern about the distributed generator type first in the system. Thank you.
Okay, thank you so much, very much, Dr. Ardyono. So maybe we discuss about the power system engineering, we discuss about the dynamic stability, discuss about transients, but not enough in 15 minutes because very interested of almost very wide area in the power system. So maybe another questions. Another questions.
I have question.
Oh,
Okay.
I have another one from YouTube.
Okay.
So just moment, Dr. Fiti. There's another
please,
one
please
people want
first. From
okay, which one?
please go on, Bu Pita from YouTube first. The question.
Okay.
From YouTube. Okay.
I couldn't find it actually. My team just said there is another question, but I couldn't find it.
Okay. Mr. Ardyono, thank you for a nice presentation. You're expert in your field, yeah. And then I just asked about the opportunity to be applied in the grid system, and also maybe for the renewable energy. Let's about the quality. Yeah. Thank you very much.
Dr. Ardyono, just only not more than 3 minutes, your answer.
Okay, so actually now we try also have actually the problem now is if we use the monitoring system actually how to collect the data, the analog data to digital data. This one is most important thing actually. So I think in that part actually, so we should collaborate it in the electrical engineering, so in our department, because in the most part in that one, actually, and our colleagues from electronic, this one is most powerful in that situation. But start from if we can collect the digital data, if this one is the good data, then the exact data actually. So we can go to the other computation, for example. So of course, if you have data, because this one is already the data, so we can make the analysis about the signal. It is one in the signal processing using the wavelet, using the or for example like Fourier, or you can be using the such kind of new method like the Stockwell transform or something. That's one is the part of signal processing. But the problem I've said, and if we use the signal processing and the data itself, the data is, for example, if we want to analyze this more deeply actually, so we need many data, for example, just for 1 second of example, so we need 1,000 data, maybe 100,000 data, etc. For this one, so it means if we calculate in the certain time, it is very fast. So we need the other method. For example, because of that, we try collaborate with the other professor, for example, is in the computer engineering like Professor Harry. This one to try using the cloud computing. Because why? Because if we already have the data, this one is far from our research actually, because this one is in the other researcher. But if we can do it, of course, the collaboration with computer engineering and person, that's one, maybe, the same as the like the Professor Natasha or something. The researchers go to that situation, I think.
Okay, thank you.
Dr. Ketut. Thank you very much.
Okay, thank you very much, Dr. Ardyono, so enough for your presentation. So this is now time, more 1 minute. Yeah. Okay, so maybe until this time, my duty as the moderator. So thank you so much, Professor Haiping, Professor Natasha, and Dr. Ardyono. So we do not get the conclusion because it's very, very different style and different major. So maybe good luck for you. Thank you so much for joining to ISITIA in Indonesia. So until times, get applause for Dr. Ardyono. Yes, just I give the time for Dr. Vita. So until this time, my duty. So thank you so much. Until next time. Bye-bye.
Thank you everyone for staying with us and also inspiring lectures we just have heard. Thank you very much. Now we are almost at the end of today's session. The head of the Department of Electrical Engineering ITS will give a closing remark. Let's welcome Dr. Dedet Riawan.
Thank you, Bu Vita. And I think to conclude all of the presentation today, it will be very difficult for me. That's why I think this will be the most challenging part in this conference. But I'm trying to be very short, very brief on this closing. Okay. First, I would like to thanks to all the participants today, because until this time we still we can enjoy the presentation from our speakers. And today we have listened from our remarkable presentation, okay, from our keynote speakers, and also some of the technical session already started this morning. And we hope all of the knowledge and the research progress experiences presented today could inspire and enrich our thought about the electrical engineering, especially in the application of the intelligence technology. And here I also see mostly the participant background is from postgraduate student. Yeah, I saw many of students attending this conference. I think it is a good sign that students still have spirit to attend this meeting, even in the pandemic situation. And my message to students: keep on the spirit and keep working with your study and your research, and good luck with the study. And also today we learn from our three distinguished speakers. The first speaker is from Professor Haiping, and we learned something very interesting, which is we can have a more comfortable car using the active suspension. And one of the comment I get from the text in the chat is, I'm afraid if the car is too comfy, I may fall to sleep while I'm driving the car. That's kind of very yes, it's a joke from one of the in the chat room. And then from Professor Natasha, thank you, because I think you give the new phrase, a new phrase today. We call a hammer and nail. I think that will be the phrase of today, hammer and nail. And still, I have to check in my dictionary what's the actual meaning of hammer and nail here. And then from Dr. Ardyono, Dr. Ardyono have introduced the large system, and then we can look deep inside the protection and impact of the stability of the large power system. And we can see how complex is the operation and protection of the large scale system until we can enjoy the electricity at our home. That's why the comment is, so if there is a power failure, we can complain about that one because there's too complex to solve. Okay, and on behalf of the Department of Electrical Engineering ITS, I would like to express our highest appreciation for all of the speakers today. And please join with us to give a big round of applause for all our speakers. Special thanks for our Rector of ITS and Dean of the Electrics Faculty for the encouraging opening speech this morning and this afternoon. Hopefully, in this we can go through this pandemic of COVID-19 safely, and hopefully everyone is in good health and safe. And also, last but not the least, of course, our appreciation goes to the organizer of this event, this seminar, because they have done a good job. It is very challenging job to have this seminar to be online. I see they working very hard during maybe the last 1 month to prepare everything here so we can gather in this forum. And finally, I would like to say have a good evening and have a good rest, and we will see you tomorrow in the second day of the conference. Thank you very much. Okay, terima kasih.
Thank you, Dr. Dedet. Now, our last agenda is the virtual photo session. If your video is still off, let's turn the video on and let's put your favorite pose for the virtual photo. We have around 9 pages of participants now, and Dr. Trihasuti will check your picture. So let's get ready.
Okay, everyone, I'll take your picture page by page. Please give your best pose. I will give instruction like a photographer. That is 3, 2, cheese. Get ready. Okay, page 1. Okay, 3, 2, cheese. Page 2. 3, 2, cheese. Next page. 3, 2, cheese. Next, 3, 2, cheese. Okay. Next, 3, 2, cheese. Next, 3, 2, cheers. Okay.
That's all.
That's all? Okay. Thank you. Thank you, everyone. That's all for the take the picture.
Okay, so that was the photo session, virtual photo session. Okay, everyone, and that photo session closed our ISITIA conference today. So we will have day 2 for technical session tomorrow. And that's all. Stay safe, everyone. See you tomorrow. Thank you very much.
Thank you. Bye-bye. See you tomorrow.
Thank you. Bye-bye. See you tomorrow.
Assalamualaikum. Thank you. Thank you.
Thank you.
Thank you. See you tomorrow.
See you on the dinner.
Lo tadi kok 9 kelihatan. Oh.
Nah, cerita dibalik.
Selamat. Sukses hari pertama. Besok sukses lagi. Nggih.
Terima kasih Pak Dekan. Thank you.
Congratulations.
Wah, selamat.
Sip. Bisa tidur ini.
Ini ya, panitia semua pada di hotel ya, Pak?
Oh iya, di hotel AJ Wangsa.
Hotel AJ Wangsa.
Rekaman.
AJ
Gitu
Bridge.
ya caranya ya.
AJ Wangsa. Ruang Bromo.
Bu Tri, tolong besok saya dikirim makanan lagi, Bu Tri.
Sukses.
Ya, terima kasih atas dukungan semuanya. Thank you everyone. The best.
Aku pasti so jepret Pepi mau tak kirim nang grup Pepi tak kirim.
Apa Pak Made?
Loh, foto bersama tadi lo tak kirim nang grup awakmu apa kita.
Oh iya dah. Aku wis motret dhewe.
Aku lagi motret awakmu dhewe ya.
Izin live ya teman-teman.
Terima kasih Pak Dekan.
Terima kasih Pak Dekan.
Terima kasih.
Pak Made.
Oi, kenapa bro?
Jos, Pak Made, Jos.
Apa nih Jos?
Fotonya Jos.
Hah?
Fotonya.
Foto apa?
Nah ini sekarang tuh.
Oh.
Sip.
Ya apa bro? Asin ojo lali, Bro, asin.
Iya, asin. Saya gak mikir asin saiki. Mikirin ujian masuk.
Wis ono bacokan iku asin.
Iya. Mikirin ujian masuk pasca.
Alah, apa dipikir ujian masuk.
Gak dipikir dilakoni, gak dipikir dilakoni.